Hi, Robin here, looking at thinking abstractly. This is predominantly aimed at the A-Level OCR Computer Science specification, though will be appropriate for the other exam boards. Basically, when we look at abstraction, first of all, so basically what actually is it? It's where we're trying to simplify a solution by looking at patterns, looking at symbols, looking at our logical steps, so that we basically just better understand it. In other words, we're taking the bigger picture and looking at the more smaller elements of it. And then by looking at it in like sort of bite-sized chunks, we can approach that problem much easier and we're much more likely to solve it in a successful manner. There are two main types of abstraction: control and data. Basically, if we think of control first of all, control abstraction is where we're looking at the logical steps. We're looking at what logical decisions are actually happening. In other words, the order that things happen in. If you think about that, that really helps you out, doesn't it? Where things are going to happen, where kind of what things has to happen before one or another. It really makes life much easier to solve as a result. When we think about data abstraction, we're thinking about what values are going to actually be used. So in other words, are we talking about sort of age? Are we talking about temperature? Are we talking about numbers? And again, what rules are then being applied to that? And the way that we then manage memory in turn. So if we look at control, like I said, we're thinking about the decision points. What we wanted to do is take down our big problem into small sections and think, well, what order do these things have to happen in? And therefore, how can we apply that in an appropriate manner? And therefore what decision points we're going to make and what we're going to use as the rules for our decision point. Is it going to be time? Is it going to be, say we're talking about a sports event, a score that's been achieved? What actually causes situations to happen? With data, like I said, we want to think about the different values that we're using and those constraints. In other words, we're going to set rules and boundaries to this. And this is really important when you think about this for validation. This is a key aspect of the NEA for the OCR, of which you really need to talk about what rules you're applying, what limitations you're applying to data, and the way that they're going to be used in turn. Another method of abstraction is to think about object-oriented programming. I have done a separate video on this, so I'll include a link to this in the description. With object-oriented programming, what we wanted to do is think again about what similarities there are. So if we think about cars in general, all cars have certain things that are true of them. So in other words, their colour, their car registration, that they have one, that they all have a make, a brand, etc. They all have an engine. We can consider those attributes. Again, we can then think about the methods that they do. In other words, the actions that take place with those cars. So in other words, with a car, they're physical things, aren't they? So movement, so left and right, braking, accelerating. If we think about this from a data point of view instead, the data could therefore be edited, or it could be sort of have rules applied to it, such as validation rules. And therefore we consider that and think about that all as one. And by grouping things together, we can sort of look for the common themes within those. But like I said, I've got a much more detailed video about this, which I'd encourage you to watch. I've also included things like Python code in there as well, which will really help you to sort of apply this in a more practical way. When we think about abstraction, it's all been brilliant so far. We've taken this problem down, we've simplified it, but we can oversimplify as well. Just a very simple example of that would be a doctor's surgery. The patient turns up and presents themselves as having pain. And then the doctor says, well, where's the pain? Oh, it's in your head. Oh, you must have a headache then, and just gives you some paracetamol. Rather than digging deeper and to understand what's the cause of that pain. Well, actually, maybe it's because the person banged their head and therefore has a cut, and therefore that cut needs to be sort of fixed in some way. So obviously we need to apply that appropriately to the situation. Therefore, we can't oversimplify. We've got to make sure we're asking enough questions that actually give us the correct answer that we're looking for. A very famous example of abstraction is Euler's bridges. So what we've got a situation of here is Königsberg is a Prussian city, a very beautiful one, and couples would want to go for romantic walks in the evening. Königsberg is famous because it's got 7 bridges. And basically the couples wanted to be able to walk across those bridges one at a time without having to recross a bridge that's previously been there. And obviously you can kind of do a full circle then, can't you? A nice walk. However, nobody could work out the order to do that in, and therefore struggled to ever sort of achieve that desire. So what Euler did was he looked at this process and tried to solve it. So first of all, he looked at the map. And as you can see from this map, it's got a lot of detail on there. There's all sorts of buildings, there's roads, there's rivers, there's bridges. It's quite hard to pick out the key information that we need. And therefore, a process we can take with abstraction is to highlight the bridges first of all, and immediately this is much easier now to see, isn't it, to solve this problem from this point. Again, if we then add colour for the river, we can really see now what's happening. We can also see where water would prevent us from being able to cross at certain points, and therefore helps us to understand again the problem much clearer as a result of that. If we then actually remove the map, we've now got a very simplified abstracted image to work with. This really helps us out. What Euler did was he then applied sort of the beginnings of graph theory to this. In other words, added nodes over each of those bridges. So as you can see, we've now got a red dot over each bridge, which represents a node, and therefore we can start to apply sort of mathematical processes to this. So once we've got our nodes, we then need to set the rules of which bridges can connect to each other, and they can be represented with each edge. And what's important to note about this is that not every bridge can be connected to another one, and therefore we're already now starting to set rules, we're starting to set criteria to this. What's also worth noting about this is that they're all bi-directional, and thus you can walk in either direction. There's no rule about that. It would only be that if you'd previously been there, that would be a criteria, wouldn't it? So we've got this, but it's still a little bit confusing to see because we're still limited by the geography. So in other words, if we then separate that and show it in a much clearer way, we've still got all of the same data being shown, we've got all of the same rules being shown, but it's much clearer now, much easier to see. And therefore we can now apply different sort of processes to this to solve the problem. Okay, so as I've said with abstraction, what we want to be able to do is apply this in real world scenarios. So by thinking of the different situations we might have. So a term you may be familiar now with programming is our variables. In other words, what pieces of memory are we going to allocate we're going to allow to be changed and to represent data, and also help us to perform the sort of execution of the system that we want to. A simple example of abstraction would be a simple map. You can see at the very bottom, very basic map there, but you could clearly follow that map to show if you wanted to get from one building to another. So the big black squares are the buildings, and obviously the thin lines are the roads. We've removed everything else. We don't need trees, we don't need ponds, we don't need any of that information, unless it was going to help us in some way. Perhaps it was a landmark or something that would be useful to sort of help you understand the process. With abstraction, what we want to do is take a big problem and separate this down. So in other words, if you think of a big problem and break that down into perhaps like the big sections of that, so that could be the management of the database, creating of the user interface, it could be handling processes of user interaction, we can separate those down into modules. Again, once we've done that, we can then break those down again into subroutines. In other words, we've broken the problem down from this bigger problem into much smaller problems as a result of that, and therefore make it much easier to program. In other words, if we program each subroutine one at a time, it helps us solve the overall process. One of the things that you need to do for the NEA is to draw a module chart, and you can see an example of one here. I've got a stock management system. It's separated out into a GUI module, a database module, and a reports module, and therefore, again, helps you to approach that. And if you imagine you doing this programming with multiple programmers, you could actually allocate each programmer a separate module to work on at the same time. And obviously, that's going to sort of speed up the process of getting the system made. Again, with the subroutines, each of those individual steps within the module can then be a challenge. In other words, rather than worrying about how to build the entire database in one go, you can think of it bit by bit. So how we're going to do the data entry, how we're going to edit data, how we're going to sort of export data. We can solve those problems one at a time rather than worrying about them all in one sort of aspect. And with a subroutine, we need to make sure we've got a clear name identifier that can be called and therefore runs that particular aspect within the program. Okay, well, hope that makes abstraction really clear for you. So thank you for watching. Please do like and subscribe this. But also, if you've got any questions at all, particularly say how this relates to the NEA, please do just add a comment and I can get back to you about that. Okay, thanks a lot.